We finally came close to methods and pipelines for further work with the architectural objects. And now you can see the result close to the final on the example of this one column. You may be wondering why we seem to have skipped the modeling stage and any talks about modularity, and why I am showing textures instead. And my answer is that it is the method of working with textures and the specifics of the shader functionality in the engine that will determine 80% of our approach to everything else. Without exaggeration, the master material or shader is a tool with which we, level artists, will interact constantly. It will set us the rules of our work, and from how gracefully and flexibly it is created depends how quickly and efficiently we will produce content. It's worth making a disclaimer here. I am not a professional technical artist. My profession is level, environment artist, and I understand some things related to shading, mostly due to my experience in different game studios. But I recommend never to trust me blindly and always consult with your technical artists before taking any of my judgment on faith. Nevertheless, I will say that the shader that I have developed and the functionality and design of which I will demonstrate today was created guided by the task to make an optimal tool close to those real solutions of AAA and AA studios. The second disclaimer concerns the functionality of Unreal Engine 5. Not only in the matter of shading, but also in the matter of modeling and lighting, Unreal Engine 5 offers us unique solutions that, on the one hand, are visually very appealing and powerful, but on the other hand, these solutions come with technical difficulties, not all of which are currently solved. My pipeline will include the use of nanite, lumen, and nanite static displacement mapping. There is this perception that Unreal Engine 5 technologies are designed to remove the technical difficulties of creating content for games, to remove the need to optimize content. And I'm strongly convinced that this is a false opinion. These technologies, as before, require updated workflows and rules of interaction with them. Until now, even the top game studios who decided to develop on Unreal Engine 5 are developing their own approaches, experimenting and making mistakes, as will we. Separately, a quick word about displacement and tessellation. I will be using, as I said, nanite static displacement mapping, although visually the effect is not much different from nanite tessellation. Static displacement works well with nanite's technology, at least as seen on the triangles viewer, cluster viewer, unlike tessellation. So far, both technologies are experimental, but I sincerely hope that at least one of them will become a mainstream and fully working method in upcoming versions of Unreal Engine 5. Nevertheless, this master material can be used without displacement, and you can achieve good results with proven methods, modeling by texture or making height map displacement in third-party applications, etc. We'll discuss this topic in as much detail as possible when we get to it in this video. Let's talk very quickly about principles and values. I identify for myself three main principles of working on level art and environment art content. These are visual quality, performance optimization, and the speed of content production. Here in the diagram, these principles are placed under the numbers 1, 2, and 3, but I wouldn't want it to be perceived as priorities. In specific developments for specific platforms and in specific games, the priorities will change slightly. So I'll just say that all 3 points are important as the pillars on which all the pipelines and workflows are built. In the future, you will see how I try to follow these principles, choose certain decisions over another, refrain from certain steps, and so on. Lastly, before we delve into the shader itself, it's worth talking a bit about the material layer system in Unreal Engine 5. And this doesn't happen to be a very popular method of working with materials in Unreal Engine, but it's actually quite powerful and has a number of advantages over the regular method. I'll talk about the material layer system briefly, but I'll leave a link to one or more videos where the topic is covered in detail. I've prepared a little diagram here, but before we go through it, let's take a quick look in the editor. And by right-clicking in the content browser, we bring up the Asset Creation menu, among which, under the Material and Layers tab, you'll see two functions, Material Layer and Material Layer Blend. These are actually material functions, but they are special functions that form a single system and work together. In addition, we will still need a traditional material, master material, where these functions will be combined. Here I have them already created in this folder. You can see at the bottom of the icons there is a corresponding node, Material Layer Blend, Master Material, where these functions are used. Let's come back here and on this board figure out how this works. We have three master functions that contain the logic itself, as well as its own node graphs. Each of the three has its own separate graph. We also have three types of instances derived from each of the master functions, with which we will change parameters, load different textures, use the shader functionality, but without changing the overall logic, which is stored, again, here in the master functions. The first master function is Material Layer. Here resides the logic of our layered material layer. I know the naming is a bit bewildering, I understand, but stick with me. Let's remember our final result. We have a layer material with 3 layers: brick, mortar, and plaster. Each of these layers is built on the logic of one master function, one material layer. Here it is. This is where we have the textures, so each of these layers is using this single material function called material layer. They differ from each other by textures and parameters, which are regulated in material layer instance, but they share the same logic, the same master function. The second master function is Material Layer Blend. This is where blending logic resides. The logic of the mask, if you will, and everything related to it. For clarity, let's take a familiar algorithm, interpolation in Unreal Engine or blend node in Substance Designer, it doesn't matter. We have A and B. These are the layers of our layered material. For example, brick and plaster. And we want to blend them using C as a mask. So this C will be material layer blend, this function. Here we will set parameters that modify the properties of our blending mask, be it something as simple as contrast or something more complex. And finally, master material. This is the standard master material that will serve us as a container for these two functions to work in. The output is material attributes node. With this material attribute layers node, we essentially create the interconnection of all the master functions right here inside master material. And the second important role for the master material is global logic. If we want to do something else with our layered material, but outside of the layers, we'll work with that here in the master material, actually after the material attribute layers. For example, from what we have already discussed, I'm going to restore the z vector of the normal map here, so that I don't have to do it separately in each layer and waste resources. Or say I want to put procedural snow on top of the layers, which is too simple in its design and doesn't require a separate layer, and so on. The material instance of the master material will be as before, as in traditional way, the asset that we will assign to the static mesh. Here it is. It will be the asset within which we will choose the configuration of layers, adjust parameters. Sometimes when working with this system, such material instance is called material layer stack. And that makes sense, especially if we look at the unique interface. Here you see layer parameters, which is largely why I love this system. To demonstrate the functionality of our shader, of course, we need some geometry first, some single unit of this architectural ensemble. And I decided to choose this column because of its simplicity. It is somewhat a standalone element, which is perfect if we don't go into the modularity conversation yet. Here you can see I blocked out the area to be dressed with slate tiles later, and I would also want to separate the bottom section of the column from the top section. This decision has its reason, which we'll go over later. I prepared a bit in advance and have already modeled out very thin chamfered edges. In addition, I have already made a UV layout. We will use two UV channels. The first channel will store the layout of the model, which we will use for the tileable textures that we talked a lot about in the last video. I'll be using texel density 1024, which is great for portfolio work. The layout in the second UV channel will be used for our unique RGBA mask, or as I call it, Splat map. In other words, the mask by which we'll be blending our layers, or the texture that determines the layer weights. This will require us to lay out in coordinates from 0 to 1, that is, making it without overlapping. However, due to the nature of Splat map, we can afford stretching, sometimes even very strong stretching, because it is to our advantage to use this space to the maximum. And stretching in this case will not be noticeable because Splat map works solely by defining layer weights. We will not see this texture by itself. So this is basically the shape in which we can send our static mesh to the engine. However, I wanted to add a little bit of detail on the corners, some chipping. I decided to do it more for the experiment to see how displacement will work on such geometry. And as you'll see later, the chipping turned out to be quite tiny, barely noticeable, but overall this concept turned out to work to a certain extent with displacement. I want to use this time to talk a little bit about the nanite concept, the nanite philosophy as I see it, and the solutions that this technology is pushing us towards. Now, you can see that I'm doing this column the old-fashioned way, as if I don't plan to take advantage of nanite. That is not the case, and you will see later what my plan is. Let me mention that I personally find questionable the idea of detailing surfaces with polygons created in third-party 3D modeling programs, Maya, Blender, ZBrush. It is acceptable for stone statues, perhaps for all sorts of organics, for rocks. It is possible, but to model flat architectural elements in a highly polygonal form, trying to recreate the irregularities of the surface, seems to me inconvenient. Working and storing many architectural modules, if they consist of 300,000, 500,000 polygons each, is inconvenient. The work with UVs in such case is inconvenient. To work in the old way, to use only really necessary number of polygons in 3D modeling applications, and to be able to quickly change, redo, or finalize low polygon static mesh, in my opinion, nothing can be more convenient than this. If we want to get surface detail with geometry, I believe for flat objects such as core architectural elements, this is only possible as a result of using displacement technology in the engine. An alternative to this existed in the form of parallax occlusion mapping, but this technology, Unreal Engine, didn't work out too seriously since a long time ago, so I would not recommend counting on it. In other engines, sometimes this technology often works quite well and creates a fairly high quality illusion of depth, eliminating the need for tessellation and displacement. However, Unreal Engine 5 went the nanite way, the way of polygons, real geometry rather than illusion, which can be interpreted as an advantage, but as I said earlier, it requires us to develop new rules and pipelines. Nanite doesn't like low polygonal objects. It loses its advantage when working with extremely irregular wireframe, like the one I have on my column with chamfered edges. Nanite likes scans. It likes waterproof, or at least continuous, pieces of geometry with a tight, uniform wireframe. But such geometry is not convenient for us, level and environment artists, to work with, especially when it comes to architecture. So when we will talk about this, remember these words of mine. We will, in Unreal Engine 5, turn our low polygonal, easy to work with, traditional geometry into almost scans that nanite will love. Our column is now in Unreal Engine 5, and while I'm looking at it, I propose the following plan of action. First, we're going to go back to the layered material system for a moment, and in particular we're going to look at the material layer node graph in detail. Remember, this is the layer logic. And finally, we're going to see how we're going to work with color for our layers. Because remember, we don't have base color map. We only have a black and white texture channel called gradient map. So let's open an existing material instance and see how it's structured. At the top we have two tabs, Details and Layer Parameters. The Details tab right here contains all the parameters of the global functions, all the things that I've output as parameters in the master material itself. The Layer Parameters tab is where my layer stack is located, and if we open the tab of any of the layers, we can access its parameters. Here's the slot into which I actually throw the material layer instance. In my case, I came up with the naming prime, referring to some basic material from my library. If we open material layer instance, from here we can get to material layer. And let's finally take a closer look at what we have here. So the graph is not complicated at all. The base is our two textures. There's a simple tiling control here. The textures we have already talked about are GRAH, which stands for Gradient, Roughness, Ambient Occlusion Height. We also have MN texture, which stands for Metallic Normal. And we have some free slot here, as you can see, which I have already defined under Generic Noise. And this noise will come in handy later for my global function called Z gradient. We'll talk about that later. And for now, I'll just rename the texture to MNG. By the way, you may have already noticed in the material preview that the normal map is not displayed. And you may have also noticed that some of the nodes we used in the previous video to restore the Z normal vector are missing now. So to clarify, I moved this operation to the master material, thus saving a little bit of computation, because if this operation was done in material layer, it would be done 4 times for a material with 4 layers. Whereas in my case, I first mix the red and green normal channels of all layers, and only then restore the blue channel. Let's move on, and here I have a small control for roughness, not the best one, maybe later I'll make a more decent function. Here, also in the future, I want to insert a small function to control the intensity of the normal map. And we'll leave this levels function, its parameters, and the result that will be our height map for later, before we talk about displacement. And now finally, we're left with color. We plug our red channel containing the black and white gradient map texture into the UV input of texture sample, thus sampling the gradient texture set in this parameter. And what is this texture? I have it named CRA brick, which means curve atlas, and we'll come back to that in a second. Here you can see the end result of this sampling, which is my base color. This is it. And it goes straight into the color parameter of one layer through the custom named reroute node, along with all the other attributes. Now back to the curve atlas texture, let's open the content browser, and if we go to the miscellaneous tab, we'll see at the top 2 options, curve and curve atlas. And first we're going to create a new curve. Let's pick a curve linear color. Rename it to your taste. I use abbreviation CRV for curve, but for now I'll just call it curve demo. And if we open it, you will see a rather simple and probably familiar concept from other graphics editing software. We have a gradient from black to white, and by clicking on the gradient bar, we create new points. For each point, we can set different colors. This is how we form our gradient, and it can be something simple or something extremely fancy. Now we're going back to the content browser and create a curve atlas. Let's name it. And you see, by default we have a resolution of 256 by 256, but there is an option here that allows you to set any resolution you want. We don't need square resolution. We'll set the resolution to 16 in width, and in height we'll set it to 1. And you see what we have, a thin strip of 16 pixels. And now on the Gradient Curve tab, we can add our curve that we just created. And now look, we can see this gradient baked onto our 16 pixels. This is the color texture that we're taking as a swatch, the one we're sampling. This may all seem confusing, and to untangle the technology a little bit, let's take a look at the process itself and create a new instance of our column material from scratch. Let's create a material instance from our master material, rename it, and put it in the appropriate folder where I store all material instances. Let's assign it to our column. It's worth assigning it to the original static mesh itself. I have this window on a different screen, I'm sorry. And let's open it up. Specifically, we're interested in Layer Parameters tab. And this is the interface where we're going to assign layers. And to do that, let's go back to my little material library here. And just to remind you, we're going to be recreating this particular material here. Now, this cylinder actually has a similar material instance assigned to it as the one we just created for the column. So we're going to have to go a little bit deeper and find the material layer instance we need, which I call prime in my library. And I don't insist on that naming, but it's convenient for me to distinguish the original material layer instance, or MLI, from the MLI variations. So having found the MLI of the brick, I can assign it to the base layer slot of my material instance for the column, and as you can see, it has become colored with the brick. You can see this little bit of chipping. It's quite tiny, could be more prominent. So in general about the material layer parameters first, all MLI parameters are changed independently in each material instance. That is, the change of these parameters will not apply to the original material layer instance. In my case, it's prime brick. This will remain untouched. But for the column, we have full control over the parameters of all layers within the material instance. You can even change the textures and get fundamentally different material, although this is not a good practice in such a system. It is desirable to create a material layer instance that will invariably be used for some significant number of material instances. Let's get back to color and gradient, and let's assign the curve atlas we created to our gradient parameter. And here we have this bizarre color, which we're obviously not happy with. Next, let's open our curve, and right on the fly we can change colors and set positions for these colors while searching for a suitable variation. I will speed up the video now, and you can fast forward if you wouldn't want to behold the process of that search. This is the result of the test gradient, and as you can see, it automatically updates Curve Atlas. What is remarkable is that all this technology is baked in, which means that in the final build, we will just have regular 16 by 1 pixel textures. And that covers it. I brought back the previously created gray gradient that matches my reference and concept, and will continue with it. And we'll continue by creating a second layer. This will be the mortar layer. It's a substance that is used to bind the brickwork together. It will protrude from the gaps between the bricks, and somewhere it will completely cover the bricks. So let's take another look at the material reference. And this is the effect that we're going for. We're going to have some bricks of gray color. This one also fits the concept. And the basic reference is also our concept art. The brick here is the same gray, unsightly brick. Then, of course, we have mortar, the one we're doing now. Mortar protruding from under the brick in layers. And finally, we have crumbled plaster in places with such an expressive indentation along the edges. So let's add mortar to our layer stack. I'm going to take an existing material from my small material library. And here's this light, rough mortar material. And just like the last time, I'll open up material instance and find my material layer instance or prime mortar inside, and I'll assign it to the appropriate slot in material instance of the column. And as you can see now, our column is completely colored with the mortar layer. Why is that? It is the second layer on top of the first one, obviously. And you see, in the first layer, the background layer, we only have a slot for material layer instance. But starting on the second layer, we have another slot, and that's just the slot for material layer blend or material layer blend instance, our blending function. For now, I'm not going to go in depth and break down the logic of this function just yet. First, let me show you how we will work with it, and later we will look inside the function and understand how it is organized in detail. So I'm going to add the material layer blend instance that's already created. And you can see a certain number of parameters displayed. We'll be particularly interested in Splat mask chooser parameter, which will allow us to select the mask texture channel. However, if you look, you won't see Splat mask itself anywhere here. I think I mentioned earlier that vertex paint doesn't suit me, and we're going to use the blending texture, RGBA set of masks, sometimes known as Splat map or Splat mask. We'll discuss all the nuances involved in this in detail a bit later, but for now I'll show you where it is. And it will be right here in the global material instance logic in details tab. You will ask why so, and I will say that it should be here because if we put this texture parameter in material layer blend, this texture, this splat mask, will be computed and processed as many times as many layers will be in our material. That is, one and the same texture will be processed each time anew for each layer, which of course we're not satisfied with. So Right now I have some default splat mask texture here, and I don't want to use it. So I'll go to the folder where my splat masks are stored and create a new texture by just duplicating the default one. And sorry for me doing it on another display. Let's open it up and we'll see this texture with RGB dots I created, just for clarity, so that is different from the usual black square. And we can see that it has pretty high resolution now, 512 by 512. We won't need such a high resolution for these masks almost at all, so we'll limit ourselves to 128 by 128. In general, you can make it even smaller, but for portfolio work, it will do fine as is. Now save everything. And now we're finally ready for blending. First, let's set the desired splat mask channel by enabling the splat mask chooser parameter. By default, we have the red channels set, and this is what we need for mixing the first and second layer. And for next layers, we will toggle this parameter further down the list. Now we select the desired object and go into the Mesh Paint Mode tab. Everyone who has ever worked with blending knows that here's the vertex color paint mode. And recently, starting with Unreal Engine 5.5, here's texture color paint mode, which we'll talk about later in detail. And finally, we have textures paint mode. In general, this tab was here quite a long time, but since this mode requires a bit of a setup and it is not strongly advertised by Epic Games themselves, it is rarely used. Although this function is pretty cool and convenient, and I will work with it. So if we press Paint, we will get access to all the tools. You see here is the slot for our paint texture, specifically our splat mask. See, it's automatically in this slot already. Sometimes you have to find it in the content browser and put it in the slot manually. The main thing is to make sure that the right texture is in the slot. Here we specify the UV channel, and I'm specifying UV channel 1 because, as a reminder, we have two UV channels on each static mesh that will work with this shader, UV channel 0 and UV channel 1. UV channel 1 is the one where the UV islands are laid out within the 0 to 1 coordinates. And this is the one we're interested in. The channel parameter here is RGBA channels that will be used to color our splat mask. For example, now I don't want to color with any other channel than red. Let's turn on the RGB channels display here and we'll see that everything is filled with black. Black is the base color that corresponds to our background layer from the layer stack. Here we have the brush size, and as soon as I start to paint, you can see we have a second layer showing up. Blending is happening. Now, what you're seeing is where I'm painting with the brush, I am manifesting a new layer. And that's not always and usually not what we're going for. What we're aiming for is a nice, controlled, correct height blend. And in our system, the influence of the height map is controlled by this color column. Which means that if we paint 100% white, i.e. we show red color on the splat mask at 100%, the influence of the height map is minimal, almost not noticeable. However, if I choose the right shade of gray for these particular layers, here you need to play a little bit and gradually lower the tone. At some point, I will get an interesting pattern, which is the result of the influence of the difference between the height maps of the lower and upper layers. And note that no matter how many strokes I do with the brush, with the mouse button pressed, it doesn't get painted further. The effect depends only on the intensity of the splat mask channel. Here it would be worth making the colors more contrasty to make it easier to see, but you can kind of see what's going on, so sorry for that. And right here on the shaded side will show better. If I want to make the gray tone even lower, closer to black, look, I'm only painting in the deepest crevices. And that's how the hide blend works. So no matter how many strokes I do with the brush around, I won't paint that spot with the top layer until I go and make the channel tone whiter. Like that. So the most interesting blending patterns are produced if we first find the most balanced intensity position on our black and white scale, and with a large brush apply a second layer with just the light strokes. The main advantage of this hide blend method is that we can get a hard border if we want, without any influence of the height map. By the way, if we want to remove the top layer, we can paint with Shift pressed, then the erase command will work. Here we have erase color set and it is black. There's also a fill button, which can also help you both fill the entire layer or delete it. I can even write letters, you see. We have such a full control over blending and can achieve very different results. And here is something to keep in mind. The resolution of our mask that we choose, 128 by 128, is not the same resolution that we're working with here in this UI. Here, we're painting at some default resolution set by the Unreal Engine 5 algorithm, and it's by default higher than 128 by 128. To see the final result with our actual resolution, we need to save our changes and exit texture paint mode. And you can see it has changed just a little bit, not much at all, but 128 by 128 is pretty high resolution for these masks. That said, it's worth understanding that a low resolution splat mask will never result in pixelation, because this texture is not used on its own. So when I say that the final result will be different from the preview, I only mean that the pattern may change slightly. No one will ever see low resolution artifacts in this situation. Now let's open up this splat mask and we can see that it's updated. There's our red channel just created right here in Unreal Engine 5. And this allows us to do all the blending right in the editor without having to spend time working with separate applications, without having to create these masks in Substance Painter, for example. However, what is remarkable is this. We can do the opposite. For example, in case of hard surface models or something sculptural or even organics, it would be more profitable to go and make such a mask in Substance Painter. Use all the generators, filters, and quickly get a cool result without having to deal with brushes. And that's the great value of such a system. It's flexible. For my historical architecture, in this example, I don't need the functionality of Substance Painter. Now, as promised, let's see how it all works. I'll open my master functions folder and here we'll find material layer blend. Let's open it up and let's see what's in here. Here we have some more logic. And let me remind you that material layer blend is a function that sets the blending logic. All the parameters that we have in our layer stack here are set in the material layer blend function, except for one parameter, the most basic parameter, the blending map itself, the splat mask. It is set in master material. Since splat mask is the foundation of our blending, let's trace its path and at the same time use its example to study the structure of the material layer system as such. Here I have a parameter called splat mask chooser to select the channel when painting. It is just component mask parameter, and splat map itself comes from the reroute node and is combined channel by channel over here. The three components, three channels, that is RGB, come from the tangent parameter. I use it just as a port to pass data between functions, not as a material attribute of the final material though. Basically, this material attribute system and the corresponding getMaterialAttribute and setMaterialAttribute nodes allow you to use material attributes simply as repositories for data to transfer. Here, see? Here I use tangent, clear coat roughness, and other attributes, but I don't use them in the material itself. They serve as a port of passing data between functions. So in my example, where do we get this data from? And going back to our splat mask, as you can see, we're pulling it from the bottom layer, meaning we're pulling it from the material layer function. And let's open up our material layer function right away and trace the entire splat mask path. And if we look at the attributes used, you won't see any tangent here, which is where we pulled the RGB texture channels from. And the thing is, it's coming from here, from input material attributes. Look, all the attributes, color, normal, roughness, and so on, which we have formed here, all this is newly set using the set material attributes node. In fact, this data is substituting some default attributes. And where do these default attributes come from? Where does this node bring them from? And they come from the master material. So the circle gets closed now, you know? And this is where our splat mask is actually located, right at the beginning of the master material. With the help of component mask, we split it into components because we don't have a free channel for float 4, only float 3 and float 2, and the tangent attribute acts as such a float 3 channel. Let's go back to material layer blend function. And here you can see I'm channeling back my 4-channel texture, combining everything with make float 4 node, and that's how it works. Now back in master material, this node here, material attribute layers, sets the default attribute values. And all those parameters and values that become your custom default are supposed to be plugged into its input. And this happens before blending and before layers. In other words, the global logic that you want to apply to materials, not after, but before blending, it will be used as an input. And as a consequence, you have to realize that any parameters that we set here, they will be outside of the layer system, but rather in the material instance itself. It's such a convoluted story, but it's all done for the good of optimization. Let's go back to the material layer blend and see first what it's all about, what it consists of by default. And here you can see two inputs, input bottom layer and input top layer, from which the function receives material attributes of the bottom and top layers respectively. Recall, these inputs essentially bring here the material attributes from our material layer function. Then I use getMaterialAttributes node to bring the various attributes here inside this function and then do certain actions with them. This is where these actions are performed. The parameters we need are set, various modulations are performed, and we'll come back to them a little bit later in detail. So after that, look, all these attributes are returned using the setMaterialAttributes nodes. They are returned back to the material attributes pool. And here is the most important operation: blend material attributes. where we blend the top and bottom layers by alpha. Here you see the reroute node, which I called blend mask, and let's take a look at what's behind it. Here is we set the splat mask and the parameter that allows you to select one of the splat mask channels, and I multiply this by 2 for, as it seems to me, better brush behavior when painting, but it is optional. And finally, the whole procedure of creating of our alpha takes place in this function. And we will talk about such parameter as outliner and its functionality a bit later. So splat mask serves as the input. There's also a softness parameter which regulates the hardness of the blending boundary. And finally, there are two reroute nodes that lead to the height maps of our layers from the alpha channels of the GRAH texture. The output we get is the actual blend mask that we will use in the alpha input of the node blend material attributes. Here we also have the mask for the outliner, which again we'll talk about later. Let's go into this function and see how it's organized. In a nutshell, what is going on here? So this function performs as a comparative analysis of two height maps, taking into account the influence of the splat mask and the ability to adjust the hardness of the boundaries of the resulting mask using the softness parameter. In other words, we're answering the question, which pixel of each height map is higher and which one is lower on the surface defined by the splat mask. I hope it makes sense. And here we first center the splat mask range by converting it from a range of 0 to 1 to a range of minus 0.5 to 0.5, and then invert the centered mask and add both separately to the height maps of the top and bottom layers respectively. And we compare the resulting sums to each other or subtract one from another with the subtract node and thus getting the difference. We then divide the resulting difference by some softness value, which will set the contrast of the blending boundary. We then set it back to a range of 0 to 1 and thus get our blending mask. And I realize I can't really get into the very bottom depth of this math and explain it better, because it is not as obvious and 100% crystal clear to myself, to be honest. And I was not the author of this method, but it is widely used, and you might find a better explanation somewhere on YouTube or in the internet if you're interested. We've talked about the height blend function. Now let's see what else we're going to do inside the material layer blend. And this node graph piece here is the opacity control function for the layers. It's pretty simple here. I'm interpolating the material attributes of the bottom and top layers by the alpha, which is the simple scalar parameter, which will run from 0 to 1. I'm using 3 separate parameters to control the opacity of jointly color and roughness, separate one for opacity of the normal, and again separately displacement opacity. And let me demonstrate how I'm going to use this. I'll mention that these parameters will be mostly needed to work with what I call soft layers. I'll explain later how they differ from regular layers, or in my naming convention, full layers. And for now, let's have a look at the already prepared example of a layer stack of 4 layers, where the last layer of this rusty grunge is such a soft layer. And we'll go into the layer parameters, specifically the material layer blend instance parameters, and here we'll see the opacity color parameter. And I already have it set to 0.5, so let's make it 0.1, and you can see the layer has almost gone. You can use the slider to find the right level of transparency for this dirt layer, which is very convenient. Just remember that it works in the range from 0 to 1, and all values outside will display incorrect color and better be avoided. So this is how the opacity function for layers is organized, and next we still have the outliner function, and we'll skip it for now as it's more of a small addition to the main functionality. And as I've already mentioned, at the end the function mixes the attributes of the top and bottom layer, taking into account all the additional features such as opacity, which we've just talked about. And this concludes the material layer blend overview. And now, to slow down the technical discussions a little bit, let's just keep painting the next layers and see what nuances we encounter. And before I do that, I wanted to show very quickly how the softness parameter from our hide blend function works. Thing is, it doesn't have the nicest response, I would say. If we inflate the value too much, it doesn't work correctly. You see, inverting the mask, doing something we don't want at all. So this parameter is very sensitive. And let me bring the camera even closer to the surface so you can see better. And see, by increasing the values just a little bit, we get this blurring of the border of the blend mask. If I move the camera away, you can see that it actually has a visual effect at a medium distance as well. I think you can clearly see right here that our mortar layer has gotten dustier, somewhat softer. I'm going to set it to the default value, and here I think I can barely see, but I still can see how the border has become more distinct, and now the material is more in line with its reference. And yet softness can be useful sometimes too. Now finally, let's add a third layer to our stack. We'll call it plaster. Again, we're just going to repeat this picture to avoid wasting time, because color selection and working with layer parameters is not a very fast process. However, in defense of this process, I will say that when you have a library of materials already created, it becomes so much easy and pleasant to work with. But I only have my references with the same gray tones at hand, so I'm not going to make anything up as I go along. So we find MLI plaster and send it to the slot in material instance. The column is now completely covered with the new layer. We will use the same blend asset everywhere, so we just call it from the previous layer. And you see right away, plaster is laying on the same places on the surface where our mortar is lying. And that's because if we go into the blend asset parameters, we see the red channel here is the default, so we need to change it to the green channel. And now the plaster is gone because we haven't painted it yet. Let's save the material and let's paint our plaster. If I press Shift+4, I'll go straight to the paint menu. Here we check the texture, everything's correct, UV channel is correct, change the paint channel to green, and from here we can paint. I will speed up the video here. Now we see that the mask has been updated and now it has a green channel. We have one last layer left, And in more than half the cases, I'm going to use a soft layer as the final layer. Let's create a new layer in material instance, and I'll reuse the grunge material layer instance from my reference column. Assign blend asset again and choose the correct channel to paint on. This time it will be the blue channel. Let's call this layer grunge and we can start painting. Let's save and see what we got. And here we see a problem. The normal map of the grunge layer overlaps the normal maps of the underlying layers. Moreover, it is obvious that the normals of this layer are flat, and that is because we're not using the MNG texture map for the grunge layer. I'll show you how this is handled in the node graph, but for now, let's see how to fix this problem in material instance. And to do this, we go back to opacity controls in the blend asset of our material instance. And here you see normal opacity parameter. We set it to 0, and basically we've disabled the normal of the last layer. Now it doesn't overlap the normals of the previous layers anymore, and by that we mimic the behavior of the least volumetric surfaces such as dust, leaks, dried salt, deposits, etc., etc. At the same time, using opacity color, and I remind you that it works together with the roughness attribute, you can achieve a neat and more balanced effect. Now let's go through material layer instance to material layer itself and see how the soft layer logic is organized. And we will immediately see that this material layer is essentially a simplified version of the full layer, the function of which we have already examined. The only difference is that here I use only a single texture, which is gradient, roughness, ambient occlusion, and height, and we have the same roughness control, we have the same low resolution texture for the color gradient. And here, see, I'm shaping the red and green channels of the normal using scalar constants and outputting the result in material attribute. This is required because our system with normal Z vector restoration will not otherwise work correctly. And that covers the soft layer subject matter as well as the blending and layering functionality overall. Now let's talk about one very important topic from a tech art point of view, however a bit distracted from my pipeline point of view. If you remember, I promised that we would talk about this tab, and we've been using the textures tab, but the thing is, starting with Unreal Engine 5.5, we have a new tab called Texture Color, and using that new system is a much more proper and optimal solution. If I was smart enough in tech art and code, I could write myself a tool that would allow me to combine this new functionality of working with the blending mask and my pipeline, in particular the way I will use displacement. So far, unfortunately, I'm not getting everything I want when working with texture color painting, but let's go through it all step by step and start from afar. Let's touch the tip of the iceberg of technical art and talk about what would be the right thing to do in our case and why. When we talk about materials and 3D graphics in general, the concept of draw call necessarily comes up. Draw call is a command that the CPU processor sends to the GPU graphics card to draw something on the screen. Every time an object with a new mesh, with new textures, with new shader parameters appears on the screen, it can be a separate draw call, a separate command. GPU, i.e. video card, usually copes well with these draw commands for models, textures, and other things. However, CPU, being loaded with all other tasks in parallel can become a so-called bottleneck. It can start delaying the sending of these commands, and then GPU capacity will be idle and graphics performance will drop, which will be expressed literally in the drop of frame rate. That's why the process of graphics optimization usually involves reducing the number of draw calls. And since we still want to have beautiful, realistic, rich graphics, our goal is to organize shaders properly and use them correctly in the future, which will kill two birds with one stone to have a beautiful picture and minimize the number of draw calls. So let's define the ideal we should strive for. Imagine that each stone element, which, based on our concept, will be textured with this material, will send only one draw call to draw the material. Once again, looking ahead, I will say that all these elements, walls, supports, foundations, all this will use the same set of layers and parameters except for the blending mask. So we won't be using the same painting between layers, of course. We're free to combine our 4 layers however we want. Somewhere it will be just plaster and grunge, for example, somewhere it will be solid brick, somewhere it will be other variation, just as it was on the concept. Since we don't change colors, layers, order of layers, or any parameters, it is in our interest to make sure that we can only use one material instance, and thus we would get one common draw call to draw that material instance. But how do we do that? Because if we go to our material instance, we see that here in the Details tab we have this Splat mask, and every time we need a new painting on the second UV channel, and we will need it roughly for each element of the architecture, we will need to copy the material instance and change the Splat mask parameter. And even though all layer parameters remain the same, with each such material instance we will add a draw call only because of this Splat mask. In general, the current Splat mask situation is not optimal and not suitable for real development. It is fine for a portfolio, but it's not good for game development. And fortunately, Unreal Engine 5.5 solved this problem. And now let's see how. Now let's go back to the very beginning of our node graph in the master material, to the Splat mask section, a texture of 4 channels which weights control the blending of layers. And this new system of painting and handling the blending map is created with these few nodes below. Let's call this function, for example, virtual splat map, because we will work with virtual textures here. The Mesh Paint Texture Object node will bring information about painting RGBA colors into the material. Next, we will need to sample this information into a texture. Here we will set UV channel 1 as default. That is in fact the second UV channel of our meshes. Next, the RGBA data goes into another node of this system called Mesh Paint Texture Replace, which essentially sets the default blending data. Here I'm just using a constant of 0, which corresponds to black color. You see, earlier I used Splat Mask Default, a black color texture, so that the material instance in the layer stack would display my very first layer, the background layer, by default. Next, we repeat the operation with the mask components to stitch this information through the layer system as before and rebuild it in the material layer blend function. Let's plug in this new system and see what we get. As we wanted, the background layer is displayed by default. In our case, it's a brick. Now let's go to the Mesh Paint mode again, this time to the Texture Color tab. By clicking on this plus icon, we can see that the paint icon has become active, but the most important thing happened elsewhere. If we go to the Details tab of the Mesh instance on the level, scroll down and we will see that the virtual texture appeared, Mesh Paint Texture. For everything to work properly, these checkboxes must be checked, and in addition,
project settings, the support for virtual textures must be enabled. Here I have enabled override index UV coordinates, that is, specify the UV channel on which we will paint and the resolution of the virtual texture. These parameters are also available in the static mesh itself. Actually, if you use this system, it is better to set them immediately in the parameters of the mesh rather than its instance on the map. You can see them here. Now let's try painting. The brush interface is the same as before. I select the red channel and manifest the second layer of material, our mortar. And as you can see, everything works exactly the same as before. Height blend responds perfectly, the same way height maps influence works depending on the color intensity of this or that channel. I must say I feel, and maybe you can also see, some subtle jittering on the edges too, but in general it doesn't affect the result. In general, everything works fine, and this method of blending, in my opinion, is 100 times more advantageous and convenient than vertex color. Now for 5 minutes of hate regarding vertex color for blending materials. Why is this mask system so much better in my opinion? First, nanite almost completely buries the benefit of using vertex color for this purpose, since it will only work when hardwired to a static mesh, and not its instance. That is, any new coloring with vertex color blending will require you to essentially make a copy of the static mesh. But the main reason why I didn't like vertex color even before nanite is that in case of using vertex color, our painting, our blending, the final result of all artistic works will change depending on the distance. As we switch LODs, the number of points decreases, and consequently the blending information will be distorted with each switch of LODs. Attempts to eliminate this are possible, of course, but tend to throw too much futile work on the artists and increase content production time. In the case of blending masks, look, what I see up close is about the same thing I see from afar. Yes, there is some mipping of textures going on. It even has a positive effect on the picture. But in general, I can paint objects in such a way that they look beautiful from all possible distances, and most importantly, look the way I want them to, the way I planned. Because quite often, I want even objects in the distance to look nice, not like smeared dummies. This is especially relevant for architecture, and for fantasy architecture even more so, when we have these huge structures which surfaces is clearly visible and readable by the eye even at a long distance, and they can occupy from 10 to 30% of the screen space and attract the eye anyway. In the case of vertex color, on the other hand, we will usually have to go to incredible pains to achieve decent visuals at a distance, and as I said, nanite drew the line at this technology specifically for blending materials in layered material. So I'll thank Epic Games for developing exactly the mask-based blending method. So we've painted mortar, and now I save this paint job and go from here. Now I've got as before an updated texture with the red channel that we just painted. Very cool, it's a virtual texture, we can double click it to open. And here is the beauty of the system. Let me bring a new column like this into the scene, straight from the content browser. I can also copy it into the scene, and you can immediately see our paint job disappearing on the new column. Here in the interface, there are copy-paste buttons that will allow us to transfer RGBA data from one mesh instance to another. In the new column, I'll also add a virtual texture and use the paste button to paste the existing colors. You have to understand that the virtual texture here is new. it has a different name. I just copied the colors, the painting itself, not the texture. And now I'm going to paint. And now I've got something going wrong, and I know what it is. The thing is that I forgot to override these two parameters to set the UV channel index and the virtual texture resolution. That is why it's correct to set these parameters right away in the static mesh details as I showed earlier, so that everything works well by default. Now I'm going to delete everything and exit the paint mode so that all the data is updated and started again. Once again I'll hit add, paste and paint, and there I can paint normally. And the point of this system is that even though I have different paint jobs, the material instance on both columns is the same. So I can do completely different things, get completely different surfaces. Let's, for example, fill an entire layer with mortar. Now I'll go through the green channel, add plaster, and look how different these two columns are. Even though we have one material instance, thus a single draw call between these two columns and any other mesh instances using this layer stack. It's a very technically cool system. However, I won't be using it. And I will go back to the previous method using Splat mask for my portfolio project. So you probably wonder, why is that? Why will I use Splat mask, even though I highly recommended using this system? And I won't use this system because I can't conveniently get my hands on this virtual texture. It is a virtual texture, and Unreal Engine absolutely intentionally creates it in the external actors folder, right here in this path. It's essentially a procedural asset, and the Unreal Engine interface doesn't provide a way to convert it to a real texture and save it in the content browser or elsewhere. Even if I open this texture, you see, I can't save it. It doesn't have any path. I can, of course, somehow copy it directly from the screen and save it in Photoshop, then re-export it back to Unreal Engine 5, but that's totally inadequately long, and I don't want to do that. But for further work, especially for work with static displacement mapping, which we will talk about in detail in the next video, I need to be able to manipulate this texture. If you want to use nanite tessellation, however, you can work with that system as it is. You don't need to extract that texture. But I want to use static displacement, and I need to be able to call this texture in the material, even if I don't use it in material attributes or blending, but I need it still for some debug function that I can turn on and off purely for operational use. I know it sounds confusing, but you'll understand it when we discuss the next steps and the displacement. In a nutshell, I always want to be able to bake the result of our blending, our combined texture. That is, get a unique texture baked onto a second UV channel for each mesh, and potentially use this texture both inside Unreal Engine or to work in third-party applications with it if needed. I think this functionality is often overlooked, and I think it is very convenient and important for producing environment art content. There is a way to bake such textures through render target functionality in Unreal Engine, but again, this blueprint refers to the material, and our virtual blend mask exists on its own. It is not mapped to the material at all. If you, unlike me, know how to write code and create custom plugins on Unreal Engine, I'm sure you can easily add to the interface the ability to bake such a texture using a virtual blend texture. But for now, I'll bring back my old feature with Splat mask, and that's where we finally close the topic of blending and layering. And in the next video, we'll break down displacement and a few additional global functions in the master material.